it's a good group. Okay, right, so here we've got the compound angle formulae, which are given in the formula booklet. And they relate A and B, so you've got a set of rules for sine, cos and tan. And what we're basically saying is that if we let A equals B, okay, we let A equal B, then the sine of 2A can be written as 2 sine A cos A, because A is B, and so both of these parts add up together. The tan of 2A becomes 2 tan A, 1 minus tan squared A, and cos 2A becomes cos squared A minus sine squared A. Now, because we also have the identity of sine squared A plus cos squared A equals 1, we can therefore substitute cos squared A as being 1 minus sine squared A, and we get the second line, 1 minus 2 sine squared A. And similarly, for sine squared A, we've got 1 minus cos squared A. If we were to rearrange that, we get 2 cos squared A minus 1. Okay? And then we've got a new set of identities which are called the double angle formulae, because they obviously relate to these parts there, 2A, and then the cos 2A. Okay? Let's see how we can now apply this to some various examples. I'll put 2 up on the board and let you have a little play around with them. So let's do this one, and in your groups, if you can have a go at this one here. Okay, and I'll put up the answers in a while. Okay, off you go. Right, we know the tan 2 theta. Let's just write down the identity. For tan 2 theta, you've got 2 tan theta divided by 1 minus tan squared theta. So there's our identity. And therefore, sine 2 theta divided by cos 2 theta. If we go back and we know for sine 2 theta can be written as 2 sine A cos A. So let's write that down. 2 sine theta cos theta divided by the identity for cos 2 theta, which is cos squared A minus sine squared A. So let's write that. Cos squared theta minus sine squared theta. Now we can see here that they want us to give something in terms of tan. And we know that tan is going to be something of the form where I've got a sine over a cos. Sine 2 theta over a cos 2 theta. I've got some sort of sine over a cos to give me a tan. And so what I'm going to do, given that I've just got this identity here, where I've got sine theta cos theta divided by cos squared over sine squared, in order to get some sort of tan, what I'm going to do is simply divide by cos squared theta, because I know sine over cos will give me that tan. So I'll write this out. I'm going to do 2 sine theta cos theta divided by, so it's the same identity, same thing here, except I'll divide top and bottom by cos squared theta, and I'll divide this by cos squared theta as well. And then we can see that the numerator, the top part, will be 2 sine theta divided by cos theta divided by the denominator, so I've got coses on both of them. Cos squared divided by cos squared is just 1. Take away my sine squared theta over the cos squared theta. But given that sine over cos is tan, we'll just get 2 tan theta divided by 1 minus tan squared theta. But we already know we've got this identity for tan 2 theta, and therefore this equals tan 2 theta. as required. Now, in this question, cos 2 theta take away 2, we can start, I mean, if we didn't have a cos 2 theta, we had some sort of cos squared theta, we can solve it straight away. Because we can let x equals cos theta, we get a quadratic equation, as you see in a second. But the problem is, we don't have theta, we've got 2 theta on one side and theta on the other side. And so it becomes a bit more difficult to play with. But fortunately, we have these double angle identities. And with the cos theta, remember, if you go back up, this is a really important point. Guys, can you make sure you take this in? With the cos 2 theta, you've got 3 different identities. Okay? And that's really important. You mustn't always assume it's cos squared take away sine squared. And you can pick what you need. Okay, so you can have the cos 2 theta in terms of sine, or in terms of coses only, or a combination of both. And it depends on the question you've got. And so that's quite a powerful thing to have. So the cos 2 theta, which one should we pick out the 3? Cos and sine, sine only or cos only? Cos only, right? Because we've got cos on the right hand side. And so let's write the identity first. Cos 2a equals 2 cos squared a take away 1. And therefore, 2 cos squared a take away 1, the left hand side, is 2 cos squared take away 1 and then take away 2. And that equals obviously the right hand side, which is 5 cos theta. If we tidy that up, we'll get 2 cos squared theta, cos squared a take away 3 equals 5 cos theta. Now at this point, we can bring everything over to one side, so you've got 2 cos squared, so I'm mixing the a's and thetas up. This should be a theta, and this should be a theta. Yeah, so this part here was just the standard identity. Okay, so we've got 2 cos theta take away 5 cos theta take away 3 equals 0. Now at this point, we can just make life easier and say let cos theta equals x, and so we've got 2x squared take away 5x take away 3. And we've turned it into a nice quadratic equation. Sorry? No, 1 minus 1 take away 2 becomes a minus 3. Now we've got a nice quadratic equation which we can factorize or solve. If we factorize it, we should get 2x plus 1 with x take away 3. And this gives us x equals 3 or x equals minus a half. If we now substitute our causes back in, i.e. cos theta equals 3, cos theta minus a half. Now, what's the problem with cos theta equals 3? Do you get a cos sign with a cos graph where the amplitude is 3? Can you get that? Right, so this is no solutions. It's not valid. So the only one we've got then is cos theta minus half. Now, what's the domain? What's the values of theta they want? Between what? What's the question tell us? 0 and 2 pi. So we need to be clear about that. Are they working in degrees or radians? Radians. And therefore, if you take the inverse of cos minus a half, can somebody give me 2 values of theta that fall within 0 and 2 pi? 2 pi over 3, 4 pi over 3. Okay, so there's your principal value and secondary value.